And he flipped the switch here, and he noticed that the needle on the galvanometer, or on the current meter, twitched. It twitched and then went back to 0. Then he opened this up, and it twitched the other direction and came back to 0. These wires are not touching each other at all. It's not like he suddenly, this is creating a current in here, because if it did, as soon as he connected the switch, they would have moved off of 0 and stayed off of 0, but all it did was it moved off of 0 and then it came back to 0. He played around with it some more, and he found that if he made it long and skinny, it didn't twitch as much. If he stuck it inside here and made it as round as possible, he got the biggest deflection from 0. Now the story is that he suddenly realized that there's this connection between, obviously, what's happening in one wire with the other wire, that there seems to be some connection with the magnetic field created by this wire that's causing a current in this wire. And the story is he was doing this in front of reporters, showing that there's this connection here that hadn't been figured out before. And a reporter asked him, of what use is this? And according to the story, although I've heard it attributed to some other physicists, he responded, of what use is a newborn child? This is the basis of all electric generation in the world. I should say in power plants. It does not cover the nails in a potato. Now, my understanding is Maxwell noticed that there was this connection here between the magnetic field, and obviously magnetic field and the area involved. It was Lentz that came up with the final mathematical formulation. It's generally called Faraday's law, although fairly, I think it should be Faraday-Lentz's law. And what he showed was that I can create a voltage or an EMF by having a change in the magnetic flux with respect to time. And that change always causes, it basically keeps the process from running away. A lot of physics textbooks that I've read usually attribute the minus sign to Lentz, but I feel like he did so much more than that. And it's possible I just don't understand the history of it. But I still think Lentz deserves more credit than I feel he deserves. Now the EMF, or this voltage, remember the relationship between voltage and the electric field. This is just E dot dl. Through a closed loop, because we do have a circuit here. So recognize the four major equations that we have at this point. We have that the electric field through some surface, through a closed surface, is equal to Q enclosed over epsilon sub naught. We have that the magnetic field dot product with a closed surface, or in other words, the magnetic flux, is equal to 0. We have that magnetic field along a line integral, or of closed loop, is equal to mu naught times the enclosed current plus mu naught epsilon sub naught d phi e dt. And then E dot dl, or the EMF, is equal to negative d phi e dt. There's a certain parallel nature to this. We have two that are dealing with either E or D dot dA, and then two of them are dot dL. They're all closed, got two closed areas and two closed loops. If they ever do come up with magnetic monopoles, basically, you probably could write out the equations that they come up with here, just come up with the right symbol for the magnetic charge, or whatever they end up calling it. But this would become the enclosed magnetic whatever, divided by mu sub naught, so forth.
For the third equation, is that phi sub E, and then phi sub B for the next one?
Yes.
Okay.
Before we go too much into this, let's talk about what the implications are. I'm going to sketch out sort of conceptually what's going on. We'll get to the hardcore math later. If I have a charge here, Q, and I move it to another spot, well, if I'm in this spot right here, notice that I have an electric field that's pointing in this direction to start with. That'd be the direction of the electric field. And then when the charge moves over here, the electric field is now moving that way. I have a change in my electric field. A change in the electric field, so change in the electric field would lead to a change in the electric flux. If I have a change in the electric flux, that would lead to a magnetic field. So by just moving that charge, I can create a magnetic field, which we knew already a moving charge does that. But this magnetic field is caused by change in the electric flux. So if I move that charge from over to this spot and then back, basically that charge, I have a change in my electric field, which would cause a change in my flux, which would cause a change in the magnetic field, which means I'd have a change in my magnetic flux. And a change in my magnetic flux means that I would actually create an electric field. I'd create a voltage which goes along with the change with an electric field. So if I take that charge and just start moving it back and forth, so these are constantly changing, ultimately, this would be constantly changing, which would lead back to there, and we suddenly have this self-propagating thing, where electric field and magnetic fields are constantly changing, creating themselves. Using the last two equations, Maxwell derives the speed of an electromagnetic wave. He finds the speed of an electromagnetic wave is 1 over the square root of mu sub naught times epsilon sub naught, which is 1 over the square root of 4 pi times 10 to the negative 7th decimeters per ampere, times 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And if someone would be kind enough to crank that out on a calculator.
$292,792,000.
790
92 meters per second.
$292? I think it was something else.
299.
$299, okay. So Maxwell gets this value here, and he realizes that's pretty darn close to the speed of light. And so he speculates. At the end of the paper where he's doing all this, he goes, I do not know if light is an electromagnetic wave, but it seems like it should be. That's too much of a coincidence. He used different wording. It's too much of a coincidence that the speed of an electromagnetic wave is the same as the speed of light. And in fact, light is an electromagnetic wave. This was an incredible breakthrough. Maxwell ultimately, I believe he lives long enough in order to get a Nobel Prize, because they don't start till 1901, and this is 1876 or so, somewhere in there, that area. Physicists thought this was great. But the majority of physicists looked at this equation and said, there's a mistake. Lorentz. And I probably should give him more fair play than I actually do. He is a Nobel Prize winner, but I think he's, from the little bits I've heard, was a grade A jackass. He's one of those people who gives physicists a bad reputation of being arrogant pricks. So, he jumps through hoops to try to explain why the mistake is not, why a certain factor is not involved in this. So close to being even greater than he was. But I'm asking you, what's missing from this equation that physicists would look at and go, you're missing something? I guess the hint is, it is the speed of an electromagnetic wave.
That it's constant? The fact that it's constant?
What do you mean that it's, what's missing then?
Like a permittivity factor?
No, not a permittivity factor. Because we have epsilon sub naught, that is permittivity.
The fact that it is, like, that it's always that,
As opposed to,
changing?
that's not the
Oh.
issue. Well,
If it's a wave, would it fluctuate, or,
no, when you talk about wave propagation, even though that there might be something moving up and down or sideways, it moves out at a certain rate. He's finding the speed at which it's moving out. You're close, Colin, and it's possible that you're thinking it and it's just not, I'm not hearing it. How fast are you moving right now? What's your speed?
Oh, like frame of reference and relativity.
There's no frame of reference here. It was impossible to think that the speed of light is always the same. This is why I wasn't quite sure how far you were taking it. There's nothing for reference frame in here. So that's 1870s. 1905, Einstein comes out with his one of 4 major papers of his from 1905. There was the groundwork for general relativity, which takes him another 10 years to get the math to back himself up. There is the evidence that air is composed of particles, and for the statistical analysis, I can never remember the 4th one, and then this one, which leads to special relativity. Einstein says, suppose there's not a mistake with this, that the speed of light is the same regardless of the reference frame. Someone turns a flashlight on, you get hit by the light going at the speed of light. Someone's driving at you in a car going half the speed of light, turns their lights on, the light's still gonna hit you at the exact same speed. Matter of fact, from the people inside this vehicle going half the speed of light, when they turn the lights on, the light's gonna leave them at the exact same speed. That the speed is the same regardless of your reference frame. What are the implications? There's a thought experiment. So we'll have the lab frame here. So in the lab frame, I've got a box, and I have a mirrored ceiling. It's just a thought experiment, so we can do this. So I have this box that's moving to the right at some speed v. It shines the light up, and because there is a sideways component to it, the light's basically going to hit the mirror, come back, and it's going to hit the box. If I look at it from a different point of view, if I look at it from the box frame, if I'm in the box, so box frame, the light's just going to bounce up and come back. If the speed is the same in both of these cases, what has to be true? Or what can't be true? It depends on how you want to look at it.
What is speed? Just classic, basic math definition.
Distance over time.
Alright. So if the speed of the light is the same in both of these cases, not this speed right here, but the speed of how fast the light is traveling, what's the implication?
Time dilation. That time doesn't travel at the same speed in both frames.
In this frame right here, the light travels a farther distance than it does here. If it has a farther distance, it's got to have a bigger time because the speed is the same in both cases. Time is not constant. That is the huge implication of this. The faster you go, matter of fact, the slower your time is. Physically. If I could travel near the speed of light, I would not age anywhere near as fast as people who aren't. And so that is the opening in special relativity. Ultimately, you can get to the point where you can derive E equals mc squared, which is potentially the most famous equation in science. We will get there. However, we do need to delay it because I just skipped over a whole bunch of stuff in order to get to this. So, any questions on this before we take a small little break and then jump back to Faraday's law, Faraday-Lentz's law, and explore that in a little bit more detail? All right, let's take a small little break here.